Well, let's consider we got an object here, and it's right near the surface of the Earth, and so that means it's some distance r from the center of the Earth. And so I want to find out force of gravity. And so we would say the force of gravity on this object, little m, Earth, I'm going to say is big M. That's going to be G little m big M over r squared, where r is the radius of the Earth. Well, we know that F equals ma. So I have an object right here. It's right near the center of the surface of the Earth. So this is the Earth right here, and this is object M. So it's some distance. It's some distance r from the center of the Earth, and so the force is going to be ma. Well, that force ma is going to be, as I said, G little m big M over r squared. So that means that the little m's cancel, so A is going to be gm over r squared. Okay, if we plug in these numbers, okay, so the acceleration 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times the mass of the Earth. We know that the mass of the Earth is 5.97 times 10 to the 24 kilograms, and then we divide by the radius of the Earth. The average radius of the Earth is going to be 6.378 times 10 to the 6 meter squared, and what we get is 9.81 meter per second squared. Well, gosh, you recognize that. That's the acceleration due to gravity. Okay. Well, gosh, that's what we just found. We found the acceleration due to gravity. So that's why it's 9.81 meter per second squared. And so that's actually a derivable sort of thing. And then the thing is, well, we've always assumed that's constant. Is it constant? Well, no, it's not constant, because that means that if you got Earth and you're looking at something that's orbiting Earth at 10,000 kilometers, so 10,000 kilometers above the surface of the Earth, then that number right there is not going to be that number right there. It's going to be a much bigger number, which means the acceleration of gravity is weaker. So why did we always say it's constant? Well, suppose you drop something from 5 meters above the surface of the Earth. Well, then this r, instead of being 6.378 million meters, it'd be 6,378,005. Well, that's changing it way out there beyond where we're ever bothering with significant figures. In fact, even if you get an entire kilometer above the surface of the Earth, you're only changing it in this fourth decimal spot. We don't go out to the fourth decimal spot here. You know, if you go up to 10 kilometers altitude, you're only barely changing that, and you're not changing it by very much, and so that's still not going to be much of a difference right here. You're going to have to go up to hundreds of kilometers before this drops from 9.81 down to like 9.8 or 9.79. So that's why we assume if you're near the surface of the Earth, this is a constant value. Okay, if you are a long ways from the surface of the Earth, it is not a constant value. Well, let's talk about Mars. Okay, so what would be the acceleration of gravity on Mars? Okay, and so you say you want to go to Mars. How much do you weigh on Mars? Okay, and so you would say, well, how do we find the G on Mars? Well, G on Mars is going to be equal to capital G times the mass of Mars divided by the radius of Mars squared. In fact, this would be true for any planet. for any object, the G, the local G, is going to be equal to G times the mass of the object divided by its radius squared. Okay, so you could do this for an asteroid, you can do it for the moon, you can do it for anything. So on Mars, then if we plug in the numbers for Mars, we get 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, okay, times the mass of Mars, 6.42 times 10 to the 23rd kilograms. Remember, when we did our previous lecture, we got 6.43 because that last digit was the least significant figure, but really it's 6.42. And then we divide by the radius of Mars, 3.39 times 10 to the 6 meters squared. So the G on Mars turns out to be 3.73 meter per second squared. Okay. Notice 3.73 meter per second squared. That turns out to be 0.38 G of the Earth. Okay, so that means you weigh 38% less on Mars than you do on Earth. So if you've got an astronaut on Mars, so you have an astronaut here, and they're in a spacesuit because the atmospheric pressure of Mars is about 1% that of Earth. Okay, so the mass here, or let's say the weight, the mg, spacesuit plus astronaut, might be 425 pounds, which means the astronaut would have a tough time even moving around on the surface of the Earth. But on Mars, it's going to be 38% of that. So that means that on Mars, this astronaut plus spacesuit would be about 162 pounds. Okay, so that's an application of what we just did here, figuring out the acceleration due to gravity on the surface of a planet. And you can work backwards too. You can also work backwards and think about it, and that is that you have an astronaut on some other planet and they drop something, they time how long it takes to hit the ground, and they find out what is G, and then you know that G equals GM over R squared. So if you could figure out how big your planet was, then you could work backwards to solve for the mass of it. So that's another way of doing it if you want to send an astronaut to another planet instead of looking something going around it. So think Stargate universe. So you step through a Stargate to another planet, and then all you got to do is drop something, measure what local G is, and if you can somehow figure out the size of the planet, then you ought to be able to figure out the mass of it.